In this video, we're going to explore special right triangles, two very common and well-known right triangles that we know some relationships for the sides just by knowing what kind of triangle they are, as well as use those properties to solve some problems. We'll start with some algebra that's going to be very useful for us in this video. Multiply 6 root 2 times root 2. When I multiply an expression with square roots together, I can multiply what's under the square roots together, I can multiply what's outside together. So I think this is 6 times square root of 2 times 2, which is 4. Square root of 4 is 2. 6 times 2, that's 12. When I see square roots in the denominator, we don't like leaving the answer like this. We want to what's called rationalize it, meaning turn this into a fraction whose denominator is a whole number. There's an easy trick for that. We're just going to multiply top and bottom by the same number, and that same number is going to be whatever square roots down below. So multiply two fractions, we multiply straight across. 6 roots of 3. Square root of 3 times square root of 3 is square root of 9. 6 square roots of 3, square root of 9 is 3. And then lastly, we can reduce 6 over 3. That's 2 over 1. So I think 6 over root 3 is better written as 2 square roots of 3. That same game here. That's a 2. And get 5 square roots of 2 over square root of 4, which is better written as 5 square roots of 2 over the whole number 2. Lastly, want to solve an equation. That means we want to get the unknown by itself, so we'll divide by square root of 3 on both sides. That's not so bad. Square root of 3 divided by square root of 3 is 1, so x is equal to this expression. We don't want to leave this expression with a square root down below, so we'll multiply top and bottom by root 3. And this will leave us with 5. Square root of 2 times square root of 3 is square root of 6. Root 3 times root 3 is square root of 9. Square root of 9 is the whole number 3. Okay, there are two main and major special right triangles, and they come from very common and very important shapes. The first one comes from a square. In particular, what we're going to do is we're going to make a right triangle by drawing in a diagonal in a square. So if here's a square that's 3 by 3, I'm going to connect the dots. You can draw either diagonal, but I'm going to draw this diagonal. And since it's a square, I know this is a right angle. And what I want to know is I'd like to know what this hypotenuse is. I can use Pythagorean theorem. That would be 3 squared plus 3 squared equals x squared. 9 plus 9 is x squared. 18 is x squared. That means that x is equal to square root of 18. I'd like to simplify. Square root of 18 isn't really apparent. There's not really a really clear connection between how would I come up with square root of 18 just by seeing this as 3 and 3. But if we simplify this radical, I think something nice pops out. If I use a factor tree maybe to simplify this, I think this is 9 and 2, 3 and 3, pair of 3's. X in this case should be 3 square roots of 2. And to me, now I notice there's something kind of weird going on here. The side lengths were 3, and the answer had a 3 in it, but it also, for some reason, had this like square root 2. Let's see if we get something similar here. Here's another square, 5, 5, and let's draw in a diagonal. And again, let's calculate this diagonal. It should be 5 squared plus 5 squared equals x squared. 25 and 25 is x squared. 50 is x squared. So that means that x is the square root of 50. And if you, again, simplify a factor tree, 25 and 2, 5 and 5, pair of 5s, single 2, 5 square roots of 2. Again, whatever the side length is showed up in my answer. The side length showed up in my length of the hypotenuse. And there's also this, but there's also this extra factor of square root 2. In general, this holds no matter what side length you have. No matter what side length you have, the hypotenuse of a triangle like this will be whatever the side length is times the square root of 2. And you can show that using the Pythagorean theorem. This kind of right triangle that we made by dividing a square in half is called a 45-45-90 right triangle. Mathematicians aren't terribly creative with how they name things. It's called that because that's what the angle measures are. When I draw on this diagonal, I split the right angle in my triangle into 2 equal pieces, and half of 90 is 45. Also, notice that for a 45-45-90 right triangle, since 2 base angles are congruent, or also because it's made from the side of a square, that it's also isosceles. So isosceles right triangles will always have this pattern of whatever the leg's length is, the hypotenuse is that length times root 2. Another special right triangle that you should know is called a 30-60-90. We make a 30-60-90 by taking an equilateral triangle this time. So note equilateral triangle. And I'm going to divide this right down the middle with an altitude. And what do you know? 60 degrees, 90 degrees, because an altitude hits at a right angle, and half of 60 is 30. There is a connection between these 3 sides. You can play kind of a similar exploration here by drawing a bunch of, buying a few of these, kind of like we did with the squares, and labeling them different numbers and trying to find the 3 parts. I'm going to, however, start with this little more general case. I'm going to say that this hypotenuse has got length of 2 times x, which means that this part that this altitude hits has split this one side into 2 equal pieces. So this would be like 1x. So if this is 1, the hypotenuse is twice as long, because the hypotenuse is a full side, or 2 of these x's together. And the question is, we'd like to know what is this side. I'm going to call it h for the height. And what is this length in terms of these other sides? Well, we know the Pythagorean theorem holds because this is a right triangle. So we can at least use Pythagorean theorem to write down something. And what I'd like to do is try to rearrange it so that h is by itself. So I think in this small right triangle, the 2 sides are x squared and h squared. And the hypotenuse is 2x. So that would be 2x squared. Let's see, what can I do to simplify this? 2x squared, I can figure out 2x squared that's 2x times 2x, which is 4 times x squared. And I'm going to get h by itself. So I'm going to subtract off this x squared. Find that h squared is equal to 3 times x squared. Or if I get h by itself, let's see, what's the square root of 3x squared? Well, I don't know what the square root of 3 is, so I'm going to leave that as a square root. I do know what the square root of x squared is. What times itself is x squared? That's x. So what does this tell me? Well, this tells me kind of similar to what's above, that if I know one of these parts, I can calculate all the others because they all are in relation to each other. So if I know what this side that's opposite of the 30-degree angle is, then to find the hypotenuse, I just double it because that's 2x. And if I know what this shortest leg is, then, well, a formula to calculate this height, or this leg across from the 60-degree angle, is just take this number, x, and then multiply it by square root of 3. In the next video, we're going to see some examples of this being calculated.